And for section 15.8, something that I like to call cylindrical coordinates. So basically, if you look at a problem like this, that looks like you would need to be using polar. So polar would be a good idea. But polar is when you have x and y. What about if you have this extra z? That's okay. You just leave z as z. So in other words, cylindrical is polar coordinates. The only difference is you leave the z as the z. So you can replace the x squared plus y squared with r squared, but dz will just stay there. Okay, so what are the limits? So this is saying that z goes from 0 to x squared plus y squared. So in other words, z is between 0 and x squared plus y squared. Then if we change this to polar, that means that z will range between 0 and r squared. So when we change it to cylindrical coordinates, these are going to be the limits for the dz part. Now this part says that y goes from 0 to that thing. So y ranges from 0 to the square root of 1 minus x squared. And if you have y equals the square root of 1 minus x squared, and you square both sides, then you'll see that this is actually talking about a circle of radius 1. Because it has only the positive square root, that means it's only the top half of the circle. So it's talking about the top half of a circle with radius 1. And then this last part is saying that x is going from 0 to 1. So x going from 0 to 1 means that we're actually only talking about this quarter of a circle right here. Okay, so then change it to cylindrical coordinates. So it's still going to be a triple integral. Changing to polar means we're still going to have r times dr d theta. The only difference with cylindrical is we still have the z information. So the limits for z, 0 to r squared. And then for r, so the radius would have to go from 0 out to 1. And last for the theta, because this is just a quarter of a circle, it goes from 0 to pi over 2. And now actually integrate. So the antiderivative of dz is going to be z, and the r will just stay there as a constant. And then z gets evaluated from 0 to r squared. So substituting r squared in for z, that's going to be r cubed. And when you substitute a 0, that's 0. So now integrate r cubed from 0 to 1. And this has no theta in it, so we could actually do the integral of the theta part also right next to it at the same time. So the antiderivative is going to be r to the 4 over 4 evaluated from 0 to 1 times, this will just be theta evaluated from 0 to pi over 2. So finally this one is going to be 1/4 minus 0. And this one is going to be pi over 2 minus 0. And so finally, the answer is pi over 8. So let's do some more fun with cylindrical coordinates. So for example number 2, how about if you just have a point 1, 2, 3? So this is x, y, and z, and change this point to cylindrical. Well, in cylindrical, the z just says itself, so the last coordinate is going to stay the same. But this is what x equals 1, and y equals 2. Well, in polar form, x is equal to r times cosine theta, and y is equal to r times sine theta. The way that I remember those is that they're in alphabetical order. X goes before y, cosine goes before sine. Now, how are we going to solve for the r and the theta? One thing we could do is divide these two. So I'm going to take this one divided by this one. So r sine of theta goes on top, r cosine theta goes on the bottom. So that means on top there needs to be a 2, and on the bottom there's a 1. And then that's good news because these r's will cancel, and then it leaves sine divided by cosine, which is tangent. So then it's just saying, when does tangent equal a 2? And for that, I could use this monstrous computer right here, and I'm working in radians. Find tangent inverse of 2. So the theta is equal to 1.107. And then what about the r? So you can now take this 1.107 and substitute it in right there, and then we could solve for r. So r times cosine of 1.107 is equal to a 1. So r equals 1 divided by cosine 1.107. One divided by cosine of 1.107, r is equal to a 2.235. So then we would have the r is 2.235, the theta 1.107, and then the z is still a 3. And there is example number 2. Next up, also just getting used to working with these cylindrical coordinates. Example number 3, instead of a point, how about a function? So change this function, x squared minus y squared plus z squared equals 1. And then change that to cylindrical coordinates. So the z can just stay the z, but replace x, and x gets replaced with r cosine theta. And then replace y with r sine theta. And then z just stays z. And then let's see if we could simplify this. So this is going to have r squared, and this is going to have r squared. So you could factor out r squared, and then it would leave behind cosine squared minus sine squared. And then I could simplify that even a little bit, because this, there's a trig identity for that. That's cosine of 2 theta. So now it has been changed over to cylindrical coordinates. If you want to, you could solve for z, but the direction said make it cylindrical, so that would be the cylindrical coordinates. And now for example number 4. Describe the graph of this function. And it is r times secant of theta equals 2. So we're going to take this out of cylindrical form and then change it to x's and y's. And then hopefully we'll be able to realize what it is once we do that. So first of all, I'm going to change secant to be 1 over cosine. And then multiply both sides by cosine. And then because this doesn't have any z in it, that means that it's going to be some type of shape. And then it's going to be that same shape as z goes up and up and up. So it's going to be some type of cylinder. And I could just use the graphing calculator in polar form to graph this, but it's more fun to do the algebra / trigonometry. So what I'm going to do next is, I know that if this was r squared, then I could replace r squared with x squared plus y squared. And there's 2 ways to get an r squared. One would be square both sides. Perfectly fine. You'll have r squared on this side, replace it with x squared plus y squared. But then this is going to have a cosine squared, and I'm not quite sure to do with that. So the other way to do it is to get an r squared, multiply both sides by r. That way on the left there's r squared, which can be replaced with x squared plus y squared. And the other advantage is this is now r times cosine of theta, so that part can be replaced with an x. And then I'm going to collect the x's on the left side, leave a little bit of space, and then say plus y squared. And right now it's equal to 0. Next up, you guessed it, complete the square. So take this number, cut it in half, and square it. That is a 1. Then add 1 to both sides. Then this part can be factored into x minus 1 squared, and then plus y squared. And on the right side, there's a 1. So that is a circle. So if you look at just the x and y coordinate system, then it's been shifted over to the right by 1. And it's a circle that has a radius of 1. So it then looks like this. Now if you graph that in 3 dimensions, then this is the x-axis, and let's say that the 1 is right here. And then make a circle of radius 1. And then because there is no z-coordinate, that means that circle goes up like this. And it creates a right circular cylinder. All right, I described the graph of it. Then, for example number 5, make it just a little more interesting. Describe this graph. And all it says is that theta goes from 0 to pi. And z ranges between r and 1. And then, what's that? Well, I know that that is half of a circle. But what is this? Well, z equals 1. So on the right side, if you let it equal it, z equals 1, that's just a plane. So that just means go up to where z equals 1 and then put a nice flat plane right there. Then what about this part? So this is saying z equals r. So if you change this to the x and y system, because r squared is equal to x squared plus y squared, then r is equal to the square root of x squared plus y squared. And then you may remember from the beginning of the semester, this is a cone. So it's a cone, and then it's getting cut off at the top when z equals 1. And then this, if it went from 0 to 2 pi, that would be the whole cone, but this is just saying half of the cone. So if you start with a cone, so a cone has straight edges, and then this is a nice perfect circle. Then cut it off at z equals 1, so cut it off here. And now it's only supposed to be half of the cone. So it's just going to be from here around to when it hits this wall over here, and then it's going to get cut off, and it's just going to be this part of the cone. So just erase that little back part right there. Well, are we ever going to do any integrating? Pienso que sí. Number 6. Find the volume between z equals the square root of x squared plus y squared, aka a cone, and if you leave off the square root, aka a paraboloid. So if you draw a quick sketch of it, so the paraboloid, I'm going to emphasize, is a little bit more rounded, and then it would look like this. And then the cone has straight edges, and it would go like this. Dot, dot, dot. So then we're supposed to find this volume that's between them. So that means that the z value is going to go from at the bottom of the paraboloid until it gets to the cone right there. So it's going to go from z equals the square root of x squared plus y squared, it's going to go from the one that doesn't have square root, just x squared plus y squared, to the red one that does have the square root. Or what if we change this to polar? Oh yeah, that's a good idea. So x squared plus y squared equals r squared. Take the square root of that. That means this one is z equals r. And then this one would be z equals r squared. So now I could start setting up the integral. And because we're finding volume, it's just going to be the dz, and then because we're changing to cylindrical, r times dr times d theta. And then z goes from this one, which was this one, which turned into that one. So at the bottom, it's r squared, and at the top, it's the one with the square root, so that's this one. Now, what about r? So because it's trapped between these two, now I need to know what r will do. So r goes from, if you project this down onto the xy plane, the very smallest, it's going to be 0 right here at the origin. And then if you project this down onto the xy plane and try to see, r is going to have to go from here over to here. So how big is that? Well, this right here is where the two meet. So that means that's when this one meets that one. So that means r is equal to r squared. And there's only two numbers that when you square it, it equals itself, namely 0 and 1. So it's going to go from 0 to 1. And then for the theta, so it's the whole volume, so you have to go all the way around this circle. So it means 0 to 2 pi. All right, we've done the hard part, setting up the integral. Now for the fun part, integrate it. So the antiderivative will be z, and that gets evaluated from r squared to r. And then don't forget the r, dr, d theta. And then when you substitute, it's going to be r minus r squared. And then it's still multiplied with r dr d theta. And now this only has r information and this only has theta information, so we could do those at the same time. So when you distribute, this is going to be r squared, and then integrate that, it's r cubed over 3. When you distribute, this is going to be r cubed. The antiderivative will be r to the 4 over 4. And then that part gets evaluated from 0 to 1. When you do the antiderivative of the d theta, that's going to be theta. And that gets evaluated from 0 to 2 pi. Substituting 1 means that it's 1/3 minus 1/4. And this one's going to be 2 pi minus 0. So 1/3 minus 1/4. So that would be 4 minus 3 is 1 over 12. So it's 1/12 of 2 pi. Or in other words, it's pi over 6. Well, that was so fun. I want to do another one. So, example number 7. So set up the integral to evaluate the triple integral of x d volume over region E, and then E is defined by z equals 0, z equals x plus y plus 5, and also cylinders x squared plus y squared equals 4, x squared plus y squared equals 9. Okay. Well, let's see. That just means the xy plane, so that's the ground. This is a plane. It got shifted up by 5, and then it's going at some kind of angle because of the x and the y. And then this is two cylinders, one inside the other. So this one has a radius of 2. So make this a radius of 2. This one has a radius of 3. And then they go up like this, up and up. And then this one goes up. Something like that. So this is the ground, so got that taken care of down here. And then this plane, well, it got shifted up by 5, and then it's going at some angle. I'm not really sure what it is, and I don't think I really have to know what it is, but it's getting cut off up there at the top. Now, set up the triple integral. Since we're using cylindrical, aka polar, then x needs to be changed to r times cosine. And then I'm going to do dz, and then we need to change it to r, dr, d theta. So z goes from the bottom to this thing. So the z will go from here up to when it hits the plane. So z goes from 0 at the bottom, and this needs to be changed to r times cosine theta, and this needs to be changed to r sine theta. Just barely got enough room for it. And then next up, what about the radius? So the radius is measured from here, and then what it has to do is it has to, at the very least, because it has to be between these two, at the very least it has to be here, and then it's going to have to extend all the way to here. So it's going to have to go from 2 to 3. So r goes from 2 to 3. Finally, the theta is the easy part. Since this circle is the whole circle, then it's going to be from 0 to 2 pi. And thank goodness it said just set it up. So now we're done.